So now we're going to be moving on to having a look at critical regions. Now, critical regions actually exist in all the hypothesis tests that we perform. If you think about when we have a look at, let's say, the values in the formula booklets, they are critical values. Critical values are the first value within the critical region. And also, if you think about when we're having a look at probabilities and we're looking at the significance level as our critical value, that is meaning that we're looking at probabilities smaller than that significance level. We are just for now going to have a look at confidence intervals with T and Z and how that can help us to find the actual critical region, not the critical region given by the probability of something happening, but by the actual value of it. So if we use the confidence interval for T and Z to help us to find a critical region for each of these distributions, the critical region is the region where we reject H0. This is useful to find if we are going to perform multiple tests and want to know which results would mean that we reject H0, so that we don't have to perform the test multiple times. So here, if we perform a two-tailed test, this is what our normal distribution looks like, where we have our accept H0 region in the middle, where we're saying that nothing has changed. This is obviously a two-tailed test because both ends have been coloured in the different colour. So the middle region is our accept H0, which we can find by using the same confidence intervals that we have just been looking at. And either side of that is where we would reject H0. And we can find that called the critical region. And it's just the parts that are outside of our confidence interval. As I just explained, this is only for two tails that we would have one at either end. If it was a one-tail test, then it would just be the values above something. And if it was the other tail, it could also be below it. So we're going to have a look at an example. So here we have a random sample of 30 households. We select as part of a study on electricity usage. And the number of kilowatts per hour was recorded for each household in a sample for the March quarter of 2006. The average usage was found to be 375 kilowatts per hour. In a very large study in March quarter of the previous year, it was found that the standard deviation of the usage was 81 kilowatts per hour. Assuming that the standard deviation is unchanged, so that means that here we are taking this to be our population standard deviation. We have 30 as our sample size. We have the mean of our sample. So we're assuming that the standard deviation is unchanged. Find the critical region for a 1% significance level test that the mean usage in the quarter of March 2006. So we are going to be using normal, as we have a sample size of 30 and we have a population standard deviation. So remember, to get the confidence interval for that, we're going to be going into dist, norm, inverse normal. We want our tail to be central. We're wanting a 1% significance level. Because we're saying unchanged, we are not saying increased or decreased. That's how I know that I'm still using central and I'm not using a one tail. My area, because it's a 1% significance level, that means that the central part is going to be 0.99. My standard deviation is going to be 81 divided by the square root of our sample size, which is 30, and my mean is going to be 375 kilowatts. So just writing that down here so that you remember. So the tail is central, because it says unchanged here. My area is 0.99, and that's because that's 100% take away 1%. My standard deviation is going to be 81 divided by the square root of 30, and that's because of this information here and here. And my mean that I put into my calculator is going to be 375, and that's because of this value here. So that gives me 336.907325 to 413.092675. So that means that if I was to do this again and end up with a value that was smaller or bigger than this interval, I would reject H0. So that means that my critical region is going to be, if we end up with a value that's less than 336.907325, or I end up with a value that's more than 413.092675. We'll have a look at another one. So here we have an industrial designer wants to determine an average amount of time it takes an adult to assemble an easy to assemble toy. We have a sample of 16 timings. This time we've got a small sample, which have an average time of 19.92 with a sample standard deviation of 5.73. So we have a small sample and we only have a sample standard deviation, which means that this time we are going to be using T. And we're having a look for the critical region at a 5% level test for the mean assembly time. So here we're just seeing if it is the same or not. So again, this is going to be a two-tail. So remember, we go into intra, T, one sample, and in this case you have no choice, you have to be using variable because we don't actually have the data, we only have a summation of the data that was used for this. Our C level is going to be 95% because we were using a 5% significance level. Our mean is going to be 19.92. Our sample standard deviation is 5.73 and our N is 16. So that gives us 16.8666985 to 22.9733015, which means that our critical region is going to be that X is smaller than 16.8666985, or the X is larger than 22.9733015. And again, you could perform some rounding with that. Values here seem to be given to two decimal places, so we could have that X is less than 87. And we could have that X is larger than 22.97. So then for our last example here, we have a topic of interest in ophthalmology is whether or not spherical reflection differs between the differs between the left and the right eye on average. In a study to investigate this, diffraction was measured on the left and right eye of 17 patients. So we have a small sample size here. The difference between the right and left eye is in die potters were D1 to D17, and elementary calculations, gave these values here. So remember that these are for our sample. So this data here is for our sample, not a population. So we have a small sample and we have some more information here about the sample, and we're trying to calculate the critical region for a difference. So again, it's going to be a two-tail one that we are now looking at. Now, because we are only given the summary statistics here, we are going to have to think back to AS, to our summary statistics section. In order to be able to find this, we are going to be having to find a sample standard deviation. And if we have a look in our formula booklet, either on page 2 or on page 4, we can find our sample standard deviation formulas there. And for this case here, we have the sum of the values and the sum of the values squared. So I believe that we are going to have to use the first formula on the fourth line down. So the sample standard deviation being the square root of 1 over n minus 1 times the sum of x squared, or in this case di squared, minus the sum of x all squared over n. So that is for our sample standard deviation. Remember that for our mean, we can just use the sum of the values divided by how many there are. That is not given to you in the formula booklet, so you have to memorise that. So, in terms of the information that we have here, our Sx becomes the square root of 1 over 17 minus 1 times, sorry I missed off a bracket there, times the sum of x squared, so the sum of d squared, which is 19.13, minus the sum of x all squared, so that's going to be minus 3.50 squared, divided by n, which is 17. And for our mean, we are going to have the sum of x, so the sum of our d's, so minus 3.50, divided by n, which is 17. So if I go back to the normal part of my calculator, so we want the square root of 1 over 17 minus 1, click across to get out of the fraction, times bracket, 19.13 minus fraction, open brackets, minus 3.5, close brackets, squared, divided by 17, across to get out to that fraction, and then close brackets. And that's another thing that I quite like about this calculator. When you are using the fraction button, you can see that the brackets, are different colours, and that helps you to make sure that you have closed all your brackets. So that ends up giving us as our standard deviation 1.072654761, and as always, we don't want to simplify that, we're going to keep that as it is. For our mean, I'll just make sure that it can't be written in a simple form, so minus 3.5 divided by 17. Again, that gives us quite a long decimal, so I am just going to be typing this in for my mean to keep that level of accuracy when I'm calculating my confidence interval. So I'm going to go back to the statistics part of my calculator. Remember, because this is a small sample and we have only the sample standard deviation, we are going to be using t. So we have to go into intra t 1 sample. Because we're looking at a 10% significance level, our C level is going to be 0.9. 100% take off 10% gives us 90%. The mean of our sample, remember, minus 3.5 divided by 17. The sample standard deviation is going to be 1.072654761. And the number of pieces of data that we have this time is 17. So that gives us a confidence interval of minus 0.660086 to 0.24832.149, which means that my critical region is going to be that x has to be less than minus 0.660 or x has to be more than 0.248 to 3 significant figures. And remember that that is looking at the difference between the left and the right eye. So I now want you to pause the video and give these 3 now you try questions a try. Okay, so hopefully you paused the video and you gave the 3 now you try questions a go. So for the first question here, we have the recommended retail price for a pair of designer jeans is £150. The price of the jeans in a sample of 16 retailers had an average of $141, and a sample standard deviation of $44. If this is a random sample and the prices are assumed to be normally distributed, find the critical region for a hypothesis test for the average sale price. So you can see here that we end up doing T because we have a small sample which is 16 and we only have the sample standard deviation, so that's how we know that it's T. Our confidence interval ends up being 117.554055 to 164.445945. So our critical region ends up being x is less than 117.55 and x is bigger than 164.45. And this is quite good because we can see what that means in a real life situation. So if we see this pair of designer jeans for less than £117.55, then they are a really good value. They're much less than what they usually are. And if they're higher than £164.45, then they're completely ripping you off. But if it's in between those two values, then it's the usual price that the jeans are. So then for question 2, we have a group of 10 foot surgery patients have a mean weight of 240 pounds. The national standard deviation was 25 pounds. So here we have the population standard deviation. So even though we have a small sample, we are going to be using normal. And then we're trying to find the critical region at 5% significance level to test for a sample that the true mean weight of all foot for surgery patients. So it is unlikely that these patients are going to be less than 224.51 or more than 255.49 kilograms. Pounds. For the third one, we were given some summary statistics. Again, we have a small sample. These summarised values that we have here are from the sample, so that means that we can only find out the sample standard deviation. So because we have a small sample and we have the sample standard deviation, that means that it's going to be T. So we have our sample standard deviation, use the formula as we did last time, gives us 6.517379695, and for oh no, I did type it in right there. Sorry, it's just because it had summarised it on the next page to less decimal places. And for the mean, we ended up with 76.3533333. I did end up just typing this fraction into my calculator instead of retyping this whole decimal here. And that meant that we ended up with a critical region of x being less than 72.744 kilograms or more than 79.963 kilograms. Now, as I stated before, these can be one-tailed when we're talking about critical regions. I've had a look at the two-tailed ones here so that you would get a feel for what they are meaning and how we figure them out. We are going to have a look at this more when we start to have a look at power and the probability of making type 1 and type 2 errors, because in that case we end up having to find the critical region quite a lot to be able to tell if we are in our reject H0 region or not. So this was just a brief look at critical regions and how we find them, especially to do with the normal distribution and the student t-test, because we've only just had a look at the confidence intervals that go along with those. So we are going to have a look at these in more detail later on. Thank you very much for listening.